Hi. It doesn't look much, does it? This is an outcrop of rock on the cliff face uh, just south of Edinburgh, on the North Sea coast there. It's a place called Sicker Point. Yet this small outcrop of rock changed the way that we see the world. Because this outcrop of rock reveals some of the immensity of geological time. And also, it shows us how geological process works. When geologists first started to come up with a systematic way of interpreting the world around them, they needed a framework, an intellectual foundation to build that on. That came from the work of a an interesting guy who lived in the late 18th century up in Scotland, a guy called James Hutton. Now, we're going to talk a bit more about Hutton's work, but you might want to watch the video clip of Sicker Point um, to show you the full importance of this particular site. This is the guy. This is James Hutton, um, a very important figure in the development of geology as a science. Now, not only does he sport a natty waistcoat, he was an original thinker. He was someone who made careful observations of the world that he saw around him, who was inspired by the uh, intellectual enlightenment that was going on in Edinburgh in the latter half of the 18th century, that really got him thinking about some of the features of the geology you can see around you in the city. Edinburgh is a place where geology is very much part of the city. There's an extinct volcano, a couple of extinct volcanoes, right in the heart of the city, for example. And he started thinking about um, how these features were there, what actually formed them. He did like a bit of a good time though, drinking, chasing women, and he did get himself into a little bit of bother with the ladies, and ended up being banished from the city to some miserable, soggy farm uh, down in the Scottish borders. But the time he spent on that farm, um, clearing out drainage ditches, watching what rivers did, watching the slow change in the landscape, made him start to realize how geology works. How the rocks he could see on the cliffs on the coast not far away, including at Sicker Point, actually um, must have been formed. Hutton's ideas, obviously, they've been refined over the time, but Hutton's ideas of what we call now uniformitarianism are crucial for our understanding of geology. What Hutton did was to link what happens today, the processes that operate today, like for example, the erosion of soil from his farmland, to the processes that operated in the past. Because what he saw in the rocks was that the features he could see um, forming actively in the Scottish borders were the same ones that happened, um, well, a huge amount of time ago. He really didn't have a grasp of exactly how long, but he did know it was an enormous amount of time. And the reason he could do that was he could see the same features in ancient rocks that we can find forming today in modern sediments. It's a hugely important intellectual leap. It seems obvious now, but at the time it was revolutionary. To see a bit more of an explanation for this, watch the first example from the Time Travelers series, part of Earth's story. It means if we can interpret the world using these uniformitarianist principles, that where we find features in the rock, like these features we can see in the image in front of you now, there should be an explanation that fits in with modern processes. Now, these features do look really quite unusual. What do you think formed them? There must be some process that we can explain through observing modern principles that will tell us what's actually happening here. Now, this could be a challenge to uniformitarianism. If we find features within the rocks that are inexplicable. Now, to show you the significance of these particular features, what I'd like you to watch now is the second example from the Earth Story Time Travelers program. And think about how the geologist that's describing these features was initially baffled by them. But it was only perhaps when he was able to travel, to see more geological processes happening, that he was able to start an interpretation. He was able to come up with a reasoned, uniformitarianist explanation for how these features formed. There is, though, a big but. We need to be careful with uniformitarianism. It's a really important idea. It's an idea that over time has stood up to testing. As geologists, we test uniformitarianism constantly. But there are features that we find within the rocks that don't form today. Let me give you a couple of examples. These unprepossessing mounds are what we call stromatolites. They don't look tremendously exciting. They are sort of an algal mat that traps sediment and will sit there very slowly photosynthesizing. Not the most exciting of organisms. However, in terms of the development of life on Earth, massively important. These things are some of the earliest complex life forms. They existed for thousands of millions of years, slowly photosynthesizing, slowly changing the composition of the atmosphere. They were thought to be extinct until a small remnant population of these stromatolites were found on a remote part of the west coast of Australia. Their abundance in the far geological past and their rarity today might make us challenge some ideas of uniformitarianism. You know, why were they able to exist in the past and yet not today? But by studying the modern environment where these things live, we can perhaps start to make some explanations. Watch the video clip on stromatolites to see a more detailed explanation of these important yet fairly unassuming organisms. Now, this is a type of rock that simply doesn't form today. This is what we call a banded iron formation. Economically, they're very important. They're incredibly rich sources of iron ore that are mined in several parts of the world uh, to provide us with really high grade iron ore, which is important as iron is a fairly low value metal, but very, very important metal. Now, these banded iron formations simply don't form anymore, and they haven't formed for hundreds, maybe 1,500 million years. Does this challenge our idea of uniformitarianism? Does this mean that uniformitarianism doesn't work? The fact that we can't go and find a modern banded iron formation being deposited? Or can we explain this in uniformitarian principles and it's simply a result of a changing environment on Earth, a changing composition of oceans and atmosphere? Watch the video clip that goes with this and see if you can decide yourself. It's clear that environments have changed over time. The atmosphere that we have now is not the same atmosphere that we had in the geological past. The ocean chemistry has changed over geological time. Continents have built up over geological time. This diagram is a cladogram showing the evolution of the plants, of land plants specifically, that had a massive influence on processes happening, particularly on the continents, in terms of the stability of sediment, in terms of the changing composition of the atmosphere. And you can see from this diagram that actually the earliest land plants only appeared in the Silurian period. Before that, there was literally no life on land. All life was in the sea. The evolution of life on land and the knock-on effects of that have had an impact on geological processes, on the rate of them, on the intensity of those processes. So, the Earth has changed over time, but can we still apply uniformitarianist principles? One of the first people to really apply these ideas after Hutton first put them out there is this guy. Another fascinating character from the early days of geology. This is a geologist called William Smith. Hardworking man. He was a mining engineer, a canal engineer, and in his work he travelled huge distances. From his diaries, they reckon he travelled maybe 10,000 miles a year. Doesn't sound like a lot in the age of cars. On horseback, that's a very long way. By travelling around so much, he started to make observations. He made observations about sequences of rocks and also the fossils he found within them. And he was able to realise there was a pattern. He was able to explain the rocks he found and their occurrence by using uniformitarianist principles. To the extent that he was able to piece together the sequence of rocks found this in England and Wales, and drew a cross-section of rock, something that really hadn't been attempted before. This particular cross-section goes from North Wales, so we have Snowdon on the left, right down to the southeast, so we've got London there on the right. Piecing together the geological history of Britain, piecing together the changing story that the rocks were telling. Now, there is a video from the BGS that explains a little bit more about his life and his work. The thing that always strikes me, though, about William Smith is his ability um, to see things that other people hadn't seen. In 1815, he published this map. This is the First Geological Map. In this map, he showed for England and Wales where you could find different types of rock. It showed the sequence of those rocks, the relationship between them. It, for the very first time, showed people what was beneath their feet. It was an absolute revolution in how we see the world. At the time, um, people didn't quite fully get it. Smith ended up bankrupt because the map that he self-published, with very little help from the sort of geological establishment at the time, didn't sell as well as he hoped. It was almost too radical. Yet, if we look at this map that Smith drew without the aid of any view of the Earth higher than from the back of a horse, and compare it to what we see today, the result of 200 years of geological research, of unimaginable increases in the technology available, and it's still recognizable. It's still a similar map. Smith's big ideas were right. He was able to take the idea that Hutton had proposed 20, 30 years before publishing this map and show how they could be used. So, to summarize, if we're going to boil the whole idea of uniformitarianism down to one key phrase, this is it. The present is the key to the past. What's happening now informs what happened on the earth in the past. The same forces drive these processes. They may have changed a bit over time, but we can still explain those away in terms of uniformitarianism. It is the most important idea in geology. Okay. As we watch the sunset over the Bass Rock, looking out across the Firth of Forth, this idea of uniformitarianism is utterly crucial to our understanding of geology. Without accepting uniformitarianism, without accepting this idea that processes today are the same ones that happened in the past, we can't interpret ancient rocks. Now, it is a theory. It's a theory, though, that is backed up. It's backed up by a logical argument. There's things that make geological processes operate now. Gravity, for example, the water cycle, atmospheric pressure changes leading to wind, for example. All of those things are the same on a modern Earth as they were on an ancient Earth. So the drivers of the processes are the same. And we can see as well the results of these processes are the same, even where we see the weird and wonderful features within the rocks. It's an idea that's been constantly tested over 230 years since Hutton first published it. And it's an idea that constantly stands up to these tests. As we'll see, as we work our way through the course, we will keep coming back to applying uniformitarianist principles. Whether that's through rock formation, whether that's through work on fossils and evolution, whether that's work on plate tectonics. All of these ultimately will come back to these uniformitarianist ideas. We do need to think about how this would relate to establishing the age of rocks and the sequence that we saw in Smith's work there, but that's for another lesson. I'll see you then.